All right, today we're going to learn about the second way of finding delta H. If you remember from last class period, we talked about the first way, which was using stoichiometry to calculate delta H. Okay, but we can calculate delta H the second way using calorimetry. Okay? I want you to have your guided notes out, and in your guided notes, there's a spot for you to write the definition for what calorimetry is. So let's take a second. I'll give you some time to write that in your notes. So calorimetry is the science of measuring what? Heat. Okay, it's the science of measuring heat. Heat can either be released in a chemical reaction or it can be absorbed. And so we're going to track that using calorimetry today. And really what we're determining is delta H. All right, a calorimeter. A calorimeter is a device used to determine the heat associated with chemical reactions. Do you have to write that in your notes?
Yes.
Yes. Okay. So a calorimeter is a device used to determine the heat associated with a chemical reaction. We're going to do a lab next time. We're going to do a lab and you're going to use a calorimeter. What we use is very simple calorimeters. They're called coffee cup calorimeters. Let me see if I can explain it so that you understand what it is, okay? We're going to use styrofoam cups, just like these, okay? We're going to use styrofoam cups with a thermometer that goes through the lid, and some of them are a bit more fancy than ours. Ours don't have a stir, but some do. Now what happens is you're going to do a chemical reaction inside the cup. Why do we have a thermometer? Well, it's going to track whether or not the temperature goes up or down in that chemical reaction. Okay, we're going to do the chemical reaction down here. If it heats up the surroundings, the thermometer will go up. If it absorbs heat energy, the temperature will go down in the cup. So why do we use styrofoam, guys? Why do we use a styrofoam cup? Yeah, it's insulated. It doesn't allow heat from the air to come in to our chemical reaction. Remember, we only want to track the heat that is released or absorbed from the reaction. So we've got to have a good insulator like a styrofoam cup. Okay? And then again, we track heat with a thermometer, with temperature. So that's kind of it's a very simple calorimeter, but it works. And so we'll do that in lab next time. Okay? Well, different substances require different amounts of heat to raise its temperature by 1 degree. Right, we could talk about wood, you could talk about plastics, you could talk about metals. All substances have a different heat capacity, which means it's the differing amounts of heat that they absorb in order to raise their temperature by 1 degree Celsius. Okay, it's called heat capacity. So please write this in your books. Heat capacity is given this symbol, capital C. It's a measure of how much heat is required to raise the temperature of the substance 1 degree Celsius. So it's the amount of heat that is required to raise its temperature 1 degree Celsius. Here's the equation that we use for heat capacity. Heat capacity is equal to the heat absorbed divided by the increase in temperature of the substance. Now we're going to stop and look at this equation for a second. Okay? What if we had a substance where you had to put in tons of heat just to raise the temperature just a little bit? So let's imagine in your minds what that means. So it takes a lot of heat, energy, in order to raise the temperature just 1 degree. Would this substance right here, let's circle it, would this substance A, would it be an insulator or a conductor? It would be an insulator. How come? You don't see very much temperature change, right? You're putting in a whole bunch of energy, but the temperature doesn't change that much. This is called an insulator. Okay, that's like a cooler. If you go camping, you want to have a good insulator there. Whether it's really hot outside, so you have a lot of energy added to it, but the temperature doesn't change that much. That's an insulator. Now let's talk about the opposite of that. Okay? What about if the heat absorbed was very small, but the temperature difference was huge? Okay? So let's call this one B. Is B an insulator or a conductor? It's obviously a conductor. How come? Why is it a good conductor, though? Well, with very little energy added to it, the temperature just increases a ton. Okay? And so you see temperature changes quite drastically, even with very little heat absorbed. Right? Okay, so that's kind of a way to explain what heat capacity is. I need to erase this because I've got some more. Okay, I've got one more term on this slide, I think. It's called specific heat capacity. Now, this one's very important to this chapter. We're going to talk about it a lot. Okay? So, specific heat capacity. It's given the symbol lowercase c. So, it's a lowercase c here.
Ours says S.
And, yes, okay, thank you. Yeah, some chemistry textbooks will use an S for the symbol for specific heat, just so it's not confused with the big C, which is heat capacity. So it's written both ways in chemistry textbooks. So if you want to put a lowercase c there, just to remind yourself. So let's talk about how specific heat capacity is different than heat capacity. So let's read the definition. It says, is the energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. What's the difference here? What's the difference of this definition compared to heat capacity? Well, the difference is now we're measuring out a specific amount of that substance. It's 1 gram of that substance. So it is more specific because it designates 1 gram of the substance. So it's the amount of heat energy required to raise the temperature of 1 gram of the substance by 1 degree Celsius. Now I want you to look at the units, okay? What are the units for specific heat? What's J? Joules. The temperature is tracked in which scale? Celsius. And mass is given with what unit? The gram. Okay, you have to be in joules and using the Celsius scale and measuring in grams, okay, for that to work. Okay, I passed out before we started this specific heat capacity table. So I want you to have that out as we go through this part of the lesson. What it does is it gives you a whole bunch of different substances. So you see a lot of different things here, right? And it gives you the specific heat. Let me move this. It gives you the specific heat of those substances. On your table, on your paper, if you're watching the notes, there is one in the guided notes or in your student workbook, but please have this out as you're watching. It'll make it easier. I want you to, on your paper, I want you to circle one thing, okay? Water right here. Put a little squiggly line around water. Okay? Water has a specific heat capacity of 4.18. 4.18. When you compare that to the other substances here, it's relatively high. So water has a high specific heat capacity. What does that mean? It's 4.18 what? Well, that tells you the amount of heat energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. It's very high, so water heats up very slowly, but it also loses heat very slowly. Okay? If we contrast that to like gold here at the bottom, gold has a very low specific heat capacity. What does that mean? Well, it heats up very quickly with very little energy, but it will also cool off very quickly. Okay? So from here to about here, what do we call these guys? These guys are good, what? They're good insulators. Please write that on your table. You know, the top half are good insulators. That means these guys are what? Good conductors. They heat up and they cool off very quickly. The insulators heat up very slowly, but they cool off very slowly. Well, let's talk about why this matters. Well, water is all over the planet, right? 70% of the surface of Earth is water. Okay? Water heats up very slowly, but it cools off really slowly. So that's why if you've ever noticed like coastal towns, their temperatures don't really change that much night to day. Even season to season, they don't change that much. And the reason for that is that right by water, which takes a lot of energy to heat up, but it holds onto that energy for a longer period of time as well. Okay. And so water takes a lot of energy to heat up and cool down. And so that's why coastal cities, their temperature stays pretty much constant throughout the day and night. They don't cool off that much at night. Or if you looked at a city more inland, like in Utah here, we see drastic temperature differences night to day. And that's because dirt, or the crust, it cools down much quicker, but it heats up a lot faster as well. So, and the differences between water and the crust, the heating, also is responsible for weather. If you look at the weather of an area, if the sun hits the ground, it heats up really quickly. What happens if the air heats up? Hot air does what? It rises. Well, if you have water next to it, it doesn't heat up that much. So some of that air comes over from the water onto the land, and it's got to replace that air that went up. And so it starts this convection current, which is responsible for the wind patterns that we see on Earth. Anyway, so there's a lot of things you can gather from this graph, but please have it out. We're going to look at the specific heat capacities of all these different substances as we go through. But make sure you know that water is 4.18. That one you got to know. Okay, let's talk about calorimetry for a second. So the energy released by a reaction is equal to the energy absorbed by the solution. When we do the lab next time, we're going to use a calorimeter just like this. We're going to do a reaction in here. There's going to be a solution in the cup. Well, the energy released by the reaction is going to heat up the water. We're going to track the temperature differences with our thermometer, so we know how much heat is released or absorbed in that chemical reaction. To find the heat energy released or absorbed in the reaction, we're going to use the following equation. Okay, this is going to be a very important equation in this chapter. I wanted to spend some time talking about what the variables mean. Okay, what does Q mean, guys?
Heat.
Q means heat. Good. Q means heat. So let's write that down. Q is equal to heat. And what are the units for heat? Joules. It's an energy value, right? M is what? M stands for mass. And which unit do we calculate mass? In the gram. Okay? C, or in some chemistry textbooks it's written as an S. It means what? Specific heat capacity. What are the units? Look on your table. What are the units? Joules per gram per degree Celsius. Okay? And then the last one, delta T. What is delta T? Yeah, change in temperature. And in what scale are we recording our temperature in? Degrees Celsius. Okay? Also, I know I've said this a lot, but delta means change. But how do you calculate change? Final minus initial. Please write that somewhere. whenever you see the delta sign, it's final minus initial. That's how you calculate it. Okay? So here we go. Q is heat, M is mass of the solution, C is a specific heat, and delta T is a change in temperature. Okay, I've got a practice problem here. Practice problem number 10. Okay, let's see if we can solve this one together. It says gold has a specific heat of 0.129 joules per gram per degree Celsius. How many joules of heat energy are required to raise the temperature of 15 grams of gold from 22 to 85 degrees Celsius? Use the equation Q equals mc delta T. Now, how I learned this equation when I was going through chemistry, I learned it as Q is equal to m cat. Okay, because the triangle here kind of looks like an A, so if you just remember m cat, you kind of remember the order that it goes in, m cat. All right, let's write that equation down. Q is equal to mc delta T. Let's plug in our variables, guys. Do we have Q? It didn't give us Q, right? So I'm going to keep calling it Q. What is M? M stands for mass. Did it give us the mass? 15 grams, so I'm going to put that in for M. 15 grams. Okay, did it tell us what the specific heat was? Yeah, the specific heat was this. So 0.129. Let's put in the units as well just for this problem. Joules per gram per degree Celsius. Goes in for C. Now when we measure change in temperature, which temperature value comes in first? Yeah, it's always, so it means final minus initial. So what was the final temperature of the gold, guys? 85. That was the final one. So it's 85 minus what? 22. Okay, so there's my delta T. But this is in degrees Celsius, so I want to put that in. Guys, what units is Q going to be in? If I have grams on top and grams on bottom, what happens? Cancel out. If I have Celsius on top and Celsius on bottom, what happens? It cancels out. So what are my units of Q going to be? Joules. Okay, let's look at the units. Now let's simplify that. 85 minus 22 is 63. Okay, so let's just times 15 times 0.129 times 63. Are you guys getting this? That Q is equal to 121.9. And again, what are my units? Joules. Okay, in this process, would you say it's an endothermic or an exothermic process? It's endothermic. How do you know that? It's endothermic because Q is positive. Heat is being absorbed. That gold is absorbing the energy. Its temperature is going up because it's absorbing energy. So that's an endothermic process. Okay, very good. Here's a question I wrote right over the top of it, but I think we can still see it. It says, how would the heat absorbed change if you had twice the mass? I need to put, how would the heat absorbed change if you added twice the mass of gold? Guys, how could we do that? If this was twice the mass, what would happen to the heat absorbed? It would double, right? It would double. So, can't think of it that way. All right, I've got some extra practice problems. I would like you guys to try this on a piece of scratch paper, okay? So, get a piece of scratch paper out. See if you can solve this problem. Remember the equation. Let's go over it. Q is equal to what? mc delta T. So if you're watching the video, please hit pause, try it. Once you have your answer, hit play and see if you got it right. Okay, let's see how you did. Hopefully, we're able to plug in our variables and solve for the answer very easily. But Anyway, let's see. Graphite has a specific heat of 0.709. So that goes in for C. 0.709. Okay? It says you have a 25-gram piece of graphite. So my grams go in for M, so 25 goes in right here. Okay. And it says it's being cooled from 35 degrees Celsius to 18. So guys, what's my final temperature here? Isn't my final temperature 18? And my initial temperature was 35? Did you guys get that right? That's the kind of tricky part about this problem. Okay, all of that is going to be equal to the heat. Okay, Q. So let's solve it. 25 times 0.709 times 18 minus 35. Okay, so Q, this is what I'm getting, is equal to a negative 301.3. What are my units for Q? Joules. Okay, now I've got a couple questions. Would this be an endo or an exothermic reaction? Exothermic. How come? Because it's releasing heat energy, right? It's releasing. Well, guys, look what's happening. This graphite cooled from 35. It was at 35 degrees Celsius. Does it have to release heat or absorb heat to get to 18? It's got to release. It's releasing heat, and that's how much heat it released. So this is an exothermic process. Okay. I've got one more practice problem on this topic. Here it is. Okay. Again, I would like you to write that equation down. Q is equal to MC delta T. Plug in your variables. See if you can solve for what it's asking. Please hit pause if you're watching the video and try it. Okay, let's see how you did with this problem, guys. It says a 40-gram sample of water absorbs 1,000 joules of energy. How much did the water temperature change? The specific heat of water is 4.18. Okay, this time it told us a couple of things. So we got a 40-gram sample, so that goes in for mass. 40 grams. But it said it absorbed 1,000 joules of energy. So joules is for Q. So my 1,000 has got to go right here in for Q. Now if it absorbed energy, guys, is my sign going to be positive or negative? Absorb means positive. Okay. And it says, how much did the water temperature change? We know the specific heat of water is 4.18. So what it doesn't give us is delta T. Let's just solve for delta T. Okay. So what I would do is 40 times 4.18. So 1,000 on this side is equal to 167.2 times delta T. Guys, how do you get delta T by itself? Yeah, let's get rid of that 167.2 by dividing it. Over here it cancels out. So my delta T is equal to 1,000 divided by 167.2. So my change in temperature is positive 5.98. And what's my units here? What's my units for temperature? Yeah, degrees Celsius, thank you. Does it make sense? If water was to absorb energy, would its temperature go up? If it absorbed that much energy, yeah, its temperature is going to go up, so that does make sense. Is this endothermic or exothermic if Q is positive? This is endothermic, right? Because the water is absorbing energy. Okay. I've got one more practice problem just to make sure that we understand this, okay? Yeah, I sense that you guys need a little more help. So let's try it. Okay, if you're watching the video, please try this one. You're going to need your specific heat table. I want you to look up and tell me what the substance is once you determine what it is. So if you're watching the video, please hit pause, try it, then hit play if you got the answer. Okay, so I started the problem. You write down the equation, Q equals mc delta T. We plugged in our variables. I times 45 by 38 and got 1710 times C. Guys, we're trying to solve for the specific heat. How do I get it by itself? Well, let's divide by 1710, both sides. Cancels out over here. So C is really equal to 4,172.4 divided by 1710. What does that equal, guys? Do you guys find that that was 2.44? 2.44. Now look at your paper, that table that I gave you with all the specific heats on it. What is closest to 2.44? Yeah, it's ethyl alcohol. That's what I would say it was. E. That substance had to be ethyl alcohol. All right, so hopefully that makes sense. Guys, I got just a couple of slides left to finish up this topic. So let's talk about calorimetry in a little bit different way. So there's this thing called constant volume calorimeter. It's called a bomb calorimeter. No, it's not in the notes, so just be paying attention to these last two slides. So there's a calorimeter that's a constant volume calorimeter. It's called a bomb calorimeter. Food industry scientists use this all the time because they want to determine the caloric properties of a food. So they always, in the nutrition facts label, they're always going to tell you the calories of the serving size. So this food item has 230 calories. Guys, calories is an energy value. It tells you how much energy is in that food item. Okay? Material is put into a container with pure oxygen. This is how they would do it in the food industry. They put it in this calorimeter, pure oxygen. Wires are used to start the combustion of that food item. And what they do is they just burn it. And they track how much heat is released from that food item. From the heat released, can they determine the amount of energy that it releases? Yes, and then from the amount of energy that it releases, they give you a calorie number. Okay? So the heat capacity of the calorimeter is also known. Because the calorimeter is going to absorb some of the heat as well, but they know that, so they can take that out of their equations. And since there's no change in volume, we're not losing energy from the expansion of gases here. So all of that can be traced back. All of the change in energy is traced back to Q, which is heat. And that's how they're so accurate with how much calories are in a food item, like a potato chip or maybe a piece of candy. They'll do the same thing. Okay. So here's an example of a bomb calorimeter. So you have a thermometer in this structure, in this calorimeter. The thermometer tracks the temperature change, obviously. They have a stirrer. It's full of water, the ignition wires. So these wires get hot, and this environment is pure oxygen. And so it just burns. Okay, and it burns, and so it's going to release heat. The heat goes into the water. As the temperature of the water increases, we can track that with temperature. And from these equations, Q is equal to mc delta T, we can get an energy value. There's a way to convert from joules to calories. And that's what they'll do in the food industry. That's how they determine how many calories are in each food item that you're eating. All right, guys, we've learned enough to do some more practice with the student workbook. So if you'll open your student workbooks to page, well, I won't tell you the page, but it's called the Specific Heat Capacity Worksheet. So please go there. It's called Specific Heat Capacity Worksheet. And see if you can't complete that. And hopefully this makes more sense.